background and requirements, which covers the what's and whys of this project. And then we'll move on to the system description and related theories, which will cover the hows. And we will finish off discussing cost analysis and the conclusory slides.
Here are the members of our group. Everyone will introduce themselves, starting with myself. My name is Daniel Hong. I am the team leader for this project, as well as the software lead.
My name is Chris Coelho-Branco. I am the hardware lead.
My name is Adrian Diaz, and I am on the computer side.
My name is Hasnath Malik, and I'm the electrical engineer.
My name is Shazib Siddiqui, and I'm an electrical engineer, and I'm on the hardware team. As we know, health safety has been an extreme concern due to the COVID-19 outbreak. The virus is spread in many different ways, and one is being human interaction. Our idea is to create a lock that can unlock and lock at certain conditions, which will limit these human interactions. So now there are many different types of companies such as Yale, August, Slate, and Tapkey who use the following technologies in their own works: Wi-Fi connectivity, Bluetooth, fingerprint scanner, number pad, RFID scanner, and voice assistant interactions. For our project, we're focusing on near-field communication. Since we're trying to minimize human interaction, fingerprint and number pads would not work. So we chose NFC, and the reason why we chose NFC over RFID and Bluetooth for many different reasons. NFC is used for a vast amount of things, such as contactless payments, sharing of information, security. It is also efficient, requires almost minimal to no time for use. And one example of NFC technology is the use of credit cards being stored on a cellular device. And as you can see here, there are some technological differences between NFC, RFID, and Bluetooth. NFC, as I have mentioned before, is efficient, and because it's due to very low range, there's almost no interaction as well. It is also fast and convenient. Our project, it could be extremely helpful in the future, especially in cases of minimizing human contact and interaction. Human contact could be made through many different actions, such as greeting, shaking hands, touching door handles. So we've had the idea of implementing a green pass and red pass system. This idea came to us with the use of green pass and red pass system that the college uses. However, our idea is to take it to a step further, and the lock will open when given a green pass, and will stay shut when given a red pass. When we're looking at it in globally, the lock can definitely impact the globe, especially during another horrific pandemic. With how quick the virus spread in the last year, human contact needed to be stopped earlier. If you're looking at it in a medical point of view, the virus cannot be stopped. Rather, we can manage the symptoms to prevent further progression. With the NFC lock, our goal is to stop the human interaction and contact. So we just want to have a quick and easy entry point with many verification steps all put into one single step.
So this is a broad overview on how we will be implementing the smart lock. We will be implementing a mobile application coded in Java that will be programmed with changeable NFC ID data. And it's going to be this data that is read by our NFC module, which comes in the form of a PN532 NFC chip. And this chip encompasses the entire user interface for this lock. And this chip passes the data onto the Raspberry Pi, which will then check the tag against a database. And depending on this interaction, it will either open the locking mechanism, in our case, an electromagnetic lock, or it will notify us, the user, that we do not have permission to open the door. And additionally, we have an emergency escape option, which is initiated by pressing the switch to use the emergency power supply to open the locking mechanism. Okay, and then on the next slide. So we can deduce the force between the electromagnet and the armature plate with the surface area S as follows on the right side using this formula. And using the fact that we have 300 pounds of force and those sizing specifications, we can determine that the total magnetic flux density will be about 3.87 times 10 to the negative 4th Teslas. And then moving to the left side, through the derivation using the Biot-Savart law, we can produce the following equation, which will show us the magnetic flux density produced by a solenoid of length L. And so we can deduce, using the derived B and implementing a 0.5 amp current, that the number of turns will be 5. And then moving on to the next slide, we see that there are two statuses associated with a relay switch, which are the normally open and normally closed, which are referring to the contacts in the circuit. And so in the normally open position, without a signal or power, the circuit remains open and then only closes once energy is introduced. And the opposite is true, where NC connection, normally closed connection, will have the contacts closed and a closed circuit, which is then released and opened only when a signal is sent to the switch. And then we can see in the next slide that there are three main kinds of uninterruptible power supplies, which are the offline, line interactive, and online types. The offline is the cheapest option to implement, but has a significant delay time in switching to the emergency power. The online is the most efficient and effective, but is very expensive, an example of which is shown in the diagram above. We decided on an offline circuit because in an emergency situation, we only need to be able to open the door and a small delay is acceptable. And as such, using a voltage regulator and the backup module shown to the right, we were able to create an emergency power supply connection. And this module on the right side simply integrates a relay switch and emergency and main power ports together onto one area for ease of use. And another important aspect of the backup power circuit was the voltage regulator. These voltage regulators use a combination of transistors like the MOSFET and amplifiers into a single integrated chip. And then this regulator then takes an input voltage and compares it to the desired reference voltage and outputs a steady voltage level as required. And interestingly enough, it can also take AC inputs and output mostly stable DC levels of voltage.
For the software design, one of the easiest ways to show code is actually through a flowchart like this. Starting with the NFC module, it'll be turned on and it'll wait for an input from our mobile device. Once it recognizes the device, it'll begin a peer-to-peer connection. The payload will be then sent from the mobile device onto the Arduino, which will be sent to the Raspberry Pi through serial. From there, it'll parse our part of the payload, including the key, and compares it with the key that we calculated using the Raspberry Pi. If they match, it'll unlock the lock and lock it again once after a few seconds. If it doesn't, the process will start over again. On the next slide is another flowchart that shows how the Android application works. Once the user opens up the app, they will be prompted to enter their login info. And once they log in, it'll send an HTTP post request to the local server, which will then reference to our local database. We will then check if the info matches the database, and if it does, it'll tell the app whether the user has a red or green pass. After it notifies them, and if it is green, they'll be prompted to press a button, which will start the NFC key, which will then output to our software. Next slide. Over here, we've created a simple mobile application for the user. It is easily modifiable, and there are currently 3 activities. The first is to allow the user to log in after they input their information into the username and password field and press the login button. The second is just a button that brings us to the next activity, which will then start the NFC peer-to-peer protocol. Next slide.
Here we have the SQL code that has been used to insert the data into the table that the app is referencing. And we have that it inserts a username, password, and the green or red pass in the form of a Boolean data type. And then we are checking from this database the info in the app.
For software iterations, we switched from using the NFC read-write mode to the peer-to-peer connection. This was because we had trouble using the read-write mode since it mainly worked with only passive items. We then tried card emulation, but that mode was actually in beta and ultimately failed in our testing. And we finally arrived at the peer-to-peer connection. There was also a number of changes done to the application. For one, we added the login screen, which we showed in 2 slides ago, which allowed us to communicate with the database. We also removed the red pass button, which we had before for debugging purposes. And since we removed it, we also had to remove the ability for red pass users to access the NFC activity. Since we added a formula, finally, we added a formula to calculate a key that changes day to day to add more security to our process.
This is a diagram of our final design, and this video that shows what that looks like in real life. The red chip is a PN532 NFC module that you can see is connected to the Arduino, which in turn is connected to a Raspberry Pi. The Raspberry Pi acts as the brains of our project. Right before the Raspberry Pi, you saw the emergency switch that we implemented in case of a blackout. Moving further down, we can see a proto board with a voltage regulator that's powering the relay switch and an emergency button. Finally, we can see the DC power switching module and a 12-volt battery, which is what makes up our backup power supply. We didn't immediately come to this design, however, and there was a lot of trial and error involved. In our first version we had presented last year, we implemented a server deadlock combination as our locking mechanism. However, we found that although initial testing went well, after stress testing the system, we found that this server would burn out in higher stress environments. We also initially connected to the Raspberry Pi to the PN532 module directly. However, we had come to realize that to use the NFC module in the P2P configuration, we would have to add an Arduino because the libraries of code that allowed the Arduino to use the P2P configuration did not work in a stable fashion on the Raspberry Pi. We didn't always have the UPS system or the emergency button either. We implemented that in the second half of this semester while carefully thinking of the use cases that our project might have. Our last iteration comes from the form of cleaning up the project up. We had many LEDs all around the project for testing purposes, and we had to make sure the signals were going where we wanted them to go. We had taken them all away to reduce power consumption as well as to reduce the number of unnecessary modules in our project as possible. These are the biggest three iterations of our hardware design. In the first, you can see the Raspberry Pi is connected directly to the PN532 chip, as well as the fact that we are still using a servo motor. In the second picture, we still have the Raspberry Pi connected directly to the PN532 chip. However, this time our locking mechanism is an electromagnetic lock coupled with a relay switch. The third it was the second to last big iteration in our hardware design. You can see that we have added an Arduino and is connected to the Raspberry Pi via USB cable for serial connection. You can also see that a voltage regulator has been added so that we can remove the breadboard power supply and use our own power supply to power both the relay switch as well as the last new component of this iteration, the emergency button. This brings us back to our final hardware design, where the only change is our addition of the uninterruptible power supply to the system. As stated before, the uninterruptible power supply was made from an AC to DC 12-volt transformer and a 12-volt battery, as well as a DC switching module.
Here we are at the NFC corrective actions and iterations. There were 3 tests to be completed on this topic. The first was a unit test to see if the NFC module would work. We deduced that the PN532 chip was successful and is still being used today. The next 2 tests dealt with the mobile application and is still and its use as a medium for NFC. Before, we used a few tags to test the input, but now we needed to make sure the application was viable. At first, we had to use the read-write mode, which wasn't great. Our point of failure was trying to use the UID for the NFC, but it is not static as we thought before when testing with our tags. For phones, a simple update can change the UID, or sometimes it's randomly generated upon request. So for our final test, we updated to the peer-to-peer mode, and that finally worked.
This was the unit testing for the PN532 chip. After testing the module with the blue key fob and white smart card, we were able to capture and use the UID information successfully.
This test was the failure test. It stemmed from the problems mentioned earlier with the UID, and we have since changed from the read-write mode to the P2P mode, as shown in the next slide, which thus shows a success as the payload was given to the Arduino, which can then be parsed out later.
Here we have the testing for the MySQL server, where we first tested a connection from the PopSQL IDE to the server, which was unsuccessful, and then we tested another connection from the MySQL Workbench IDE to the same server, and it proved successful.
Here is the test that we made for the login activity. We simply matched up the information that was set on the database, and a toast will tell us whether the user and password was correct or if there was an error. And it would tell us if there was a green pass or red pass if it was successful.
This was the first integration test of any kind of UPS system. This test included a UPS uninterruptible power system that we had made from scratch, containing diodes and capacitors. Something had gone wrong, however, and we're not 100% sure what, but we had caused a small fire when we tried to hook up the system. No one was hurt in the fire, but it did leave us with a small scare. Our next iteration of the UPS system, we decided to use the DC backup battery switching module instead of trying to build it ourselves for our safety and for the sake of practicality, because the board had already been made. There was no point in trying to reinvent the wheel. We had tried to integrate this into our system, and we were met with success, and the lock engaged as it should have.
Throughout the course of the spring semester, we were able to achieve the previously set goals and managed to produce a functioning prototype to showcase the proof of concept. In the near future, the project may only require some minor changes, such as optimizations to the circuitry, tweaks to the design to increase aesthetics to improve client satisfaction, and some coding optimizations to rid the program of redundancy and increase runtime efficiency.
This is a timeline that we had proposed in the beginning of this semester. We had built in buffers just in case anything had gone awry. We'd learned about that over the last semester. We are pleased to announce that we were able to follow our timeline relatively well, and we have finished all the tasks that we needed up until now.
During the course of this project, there were several challenges that needed to be overcome, both on the hardware and software side of things. These challenges warranted us to expand our knowledge into new topics, such as voltage regulators, relay switches on the hardware side, and on the software side, we had to learn SQL, PHP, and Android Studio, as well as NFC connectivity on both the hardware and software side of things.
This is the breakdown of costs and materials that we had used. We would like to at this time thank Visha for sponsoring us and buying us most of the materials to test and prototype this project. And this is what our finished prototype would look like. And this is the prototype in action. As you see, at first the door is locked, and now you see me pick up a phone and enter in Daniel's information into the app that we had created. Here you see me struggle with the touchscreen a little bit because I have fat fingers. Now I have a green pass, and you can see me put the phone close to the NFC reader, touch the screen to Android beam the NFC payload and the door unlocks. You can see here after a few seconds that the lock re-engages and the door is locked again. The big red button at the top is acting as our emergency switch, and as you see now, when I press the switch, the lock disengages again, and when I twist the switch back up into its original position, the lock re-engages.
Here are the code standards and constraints that we followed through this project. The ISO 14443 standard is for RFID and NFC interfaces, mainly for RFID tags, and which are used in proximity systems and is aimed for use in payment systems. The second one listed is the ISO/IEC 18092/ECMA-340, which is based off of the previously mentioned ISO 14443, but is specifically for NFC or near-field communication, its interface, and its protocol. This standard will tell us about the coding, transfer speeds, initialization schemes, and more for both passive and active NFC nodes. Finally, we use the IEEE 802.11, which is a standard for Wi-Fi and HTTP/1.1 in order to get the phone to communicate with our local server and database.
Through the design process of our project, we were focused on the safety and security of our users. The project as an implementation itself was to help institutions keep their staff and clients safe by providing them with a contactless option. In the testing phase, we realized it could be possible for a user to accidentally scan their credit card or something equally confidential. We made sure that our software does not save any of this scan data for any longer than it takes to check the database if it's a valid pass. It also implemented code which would allow our user to take the scanner completely offline to minimize any chance of a hacker trying to get into it, with the only reason to bring the system back online to be for maintenance purposes. In our wireless implementation of this project, when the Raspberry Pi is connected to through Wi-Fi and not through internet, we use the IEEE standard for wireless communication, so we're not transmitting any data in any insecure fashion. One consideration we're still trying to resolve is the misuse of our project. Theoretically, our project could be modified to be implemented to cause discrimination against the population, even when this was never the original implementation. We have no solution to that as of right now.
As for engineering complexities, one of the sub-problems, as has been mentioned numerously, was the NFC and Android problem. It was pretty difficult to work around, and we failed to use the read-write mode, and then we tried using card emulation since it was similar to how we tested with the tags. However, there wasn't much documentation on this since it was technically in beta. Many forums had questions, but no direct answers. They ended up telling us to try to use peer-to-peer just like Android Beam.
We'd originally tried to regulate one power supply to the entire system, including the Raspberry Pi and the Arduino Uno. This had led us to try to make crazy circuits trying to optimize the currents. We realized halfway through the project that if we try to implement that circuit, we would have just been spinning gears, as we wouldn't have been optimizing a single thing. We then iterated to using a separate power supply for the microcontrollers, then from the locking mechanism.
The disciplines we utilized in creating this project are software engineering, and computer science in design of the app and programming of the Arduino/Raspberry Pi. We also used electrical engineering for the circuit design, and finally, we utilized mechanical engineering and physics for part selection, as well as mechanics surrounding the lock.
This is our table of references that we used to create this presentation.
We would like to give a special thanks to Professor Sultan for helping us throughout this project and being very supportive in our journey of completion. And a thank you to all you for listening to the presentation. Are there any questions?
Thanks, guys, for your presentation. You did really a good job here. Thanks all of you for giving the